Welcome to Prayer Exercise number 134, and today we're finishing off the second half of this podcast series. So the first half looked at this thing called a Bionic Airfoil, and today we're going to be looking at the second half of this. So we're going to be looking at a paper called Numerical Simulation of Flow over a Bionic Airfoil. So what is this Bionic Airfoil? Well, it comes from nature, as you might expect with the name bionic, and it's inspired by birds, for example. So birds have a wing, obviously, two wings, one on each side, and often in the inboard part of the wing, as we can see in figure 1 here, there are these feathers that often pop up, and these feathers act effectively like a second surface over the top of a bird's wing. And these researchers were interested in how this affects the airfoil, how this affects the performance of these airfoils. So if you were to put this on an airfoil that they use here, which is HQ17, this type of airfoil, which is quite thick. The thickness, maximum thickness is like 15%, which occurs at around 42% of the cord. And it's also a little bit cambered at 4.2%, something like that, at 40% of the cord as well. And this is an open access paper, by the way, so you can find this in the link in the description. So with the last podcast, just to recap, if you haven't listened to that, go back to listen to that. If you want to, if you've already listened to that, I'm just going to recap it now. So they used CFD to investigate this airfoil and how this flap affects the aerodynamics of this airfoil. They looked at a few different configurations. So this flap is effectively just this like horizontal plate that comes out at the back over the top of the airfoil. So here they have it starting at 80% of the cord, and they pitched it at different angles. So they went from like pitching it up to pitching it down, then also having different general shapes of this flap to being an S shape. So we have in, let me scroll down, here we go, figure 10. We have an S shape with the peak closest to the airfoil and then the trough closest to the airfoil. And look at all these different parameters. So basically, they found that if you have the airfoil pitched up at an angle, so here they have up to 12.14 degrees, that is going to affect the airfoil's performance more than if you pitch it down. This pretty much makes sense because if you have this airfoil, this flap pitched up, you're effectively going to be getting a bigger wake from this flap. So that doesn't necessarily mean that it's good, but it can be good depending on the situation. What they found typically was that these flaps generally reduce the lift and increase the drag at pre-stall angles of attack, so that's bad. But at post-stall angles of attack, this flap typically increases the lift and reduces the drag. So in other words, it typically delays stall. And the higher this flap is pitched to, the more that it will delay the stall. They also found that with these S-shape flaps here, that typically the one where you have the trough to begin with and then the peak, that performs significantly better than the one where you have the peak first, then the trough. And the one with this is called S2 compared to S1. So S2 is the one with the trough first. And this S2 profile typically is more similar in performance to the horizontal flap without any of these curves than the peak. However, that does really depend on other parameters, which we'll look into today. So let's scroll down to what we're looking at today after this recap. And here is what we're looking at. So in figure 13, we have 3 different positions for this flap. They still start at 80% of the cord, but they are either pretty much completely connected to the airfoil or they're staged off of the airfoil a little bit. So there is a gap between the airfoil suction surface and this horizontal flap where the flow can flow through in between. And then there's one in the middle called P1, which is still, there's a gap between the suction surface and the horizontal and this horizontal flap, but it's not as great a gap as P2, which is the most extreme. So they wanted to see what would happen here if you have this gap here for the flow to be able to bleed through. Now P0 is almost attached. That's the closest flap to the suction surface. P1 is staged 0.08% of the cord off of the surface, and P2 is double that, so 0.16% of the cord. Now they've used the cord to non-dimensionalize these distances. I'm not sure if that's the best way or the worst way. I'm not really sure. It's just a way of non-dimensionalizing this geometry. Another way would be potentially looking at the boundary layer height and non-dimensionalizing the distance of this flap to the surface, I think, because I'm pretty sure the boundary layer height will make a big difference. For example, with P0, which is almost completely connected to the airfoil surface, there's not much of a gap for like the clean flow to get through. So you really only going to be getting this boundary layer flow, which is quite slow moving fluid, moving through here, which means that information of the flow can't really move upstream or downstream as quickly as if you were to have like P2, for example, where you have a much greater gap between the airfoil suction surface and the horizontal flap. Again, that's just one idea that I had where you can potentially non-dimensionalize these heights from the airfoil surface in terms of the boundary layer thickness. Now, another thing with these flaps is that they're tilted down a little bit, which we found from the last podcast, 133, that reduces the effectiveness of the flap a little bit. So figure 14 shows the effects of these flaps in these different configurations with angle of attack. So I'll zoom out a little bit so you can see this. And if you're just listening to this, you can watch it on Spotify and or YouTube. And on YouTube, we have other goodies as well you can find for aerodynamics. So for these flaps in the pre-stall regime, they pretty much all show the exact same effects. Like you can see the lift here, there's almost no difference in terms of its performance. They always reduce the lift of the airfoil in the pre-stall angles of attack. And that is accompanied with an increase in the drag coefficient in the pre-stall angles of attack. And again, there's very little difference between these flaps. So in the pre-stall angles of attack ranges, the flap height does not really make much of a difference. You can like put it off quite a distance from the airfoil surface and still get a very similar performance. So why are we getting these effects to begin with in the pre-stall angles of attack? Well, it pretty much just comes down to the airfoil with this flap just making the flow separate. So I'll quickly jump over to Paint so I can draw this for you and show you what I mean by that. So let's get Paint up here. Okay, so we've got the drawing tool. Let's say we have the airfoil top surface here. Then we have the flow coming over the top. This is the boundary layer. Then we have this flap coming out. Well, if there is a flap, the flow is going to be coming over the top, and then it's going to separate here, and then it's going to be a much bigger wake in the back region of the airfoil, downstream of the airfoil. If we had no flap, then the flow, even if it does separate, it's likely that it's not going to be separating nearly as greatly as over the airfoil with the flap. So it might separate here, and then we get a bit of a wake here. So this wake region here is smaller than this wake region here. That's why we would probably get more flow separation. And at low angles of attack, we don't really get much flow separation over the airfoils to begin with anyway. So this flap definitely exacerbates how much separation we're getting, and that's why we get this reduced lift and increased drag, because we have this last part of the airfoil that's not really producing lift and it's increasing a big wake, so that's a lot of pressure drag. Now at the stall angle attack and postal angle attack, the airfoils with these flaps are always pretty much benefited by them. So these flaps are always increasing the lift and reducing the drag. So that's going to increase the lift to drag ratio a lot, which means that the airfoil is becoming more efficient. So why does that happen? Well, for a similar reason is that with this flap, we're kind of segregating the back part of the airfoil, which means that the flow might still separate in the exact same kind of manner as when we had the flow and we had the angle of attack of 5 degrees for this flap situation. But it can't really progress more than that because we have this flap segregating the separating region from the rest of the airfoil. With the airfoil with no flap, well, when you increase angle of attack, obviously the flow separation zone can migrate upstream and we get more of the airfoil in the separated flow region. So that's why we get this positive post-stall effect. Now, in the post-stall effect, we can see that the greater the gap between the flap and the suction surface, the less effective this flap is in affecting the aerodynamics. So the lower the lift coefficient and the higher the drag compared to the baseline case. But it's still better than no flap at all. So we see here P2, which is the red dashed line for both the drag and the lift graphs. We can see that the effects that it has on the airfoil is significantly less than P0, which has the flap pretty much completely on the airfoil surface, which is significantly higher. But it's still better than the baseline. So we can see that it does increase the lift and reduce the drag quite a bit compared to the baseline airfoil, which is this solid line here. So in other words, having a flap, regardless of how high it is from the airfoil, is usually better than having no flap. Obviously, they'll get to a point where you have if you have a 10 centimeter or 50 centimeter gap between the airfoil surface and the flap, that's going to probably result in the flap having no effect, but that's quite a distance off. Having a few millimeters or even a centimeter is still close enough for this flap to have a good effect on the airfoil surface. Now, why does this airfoil? What I thought was that it is likely that this flap is not shielding the upstream boundary layer as much from the adverse pressure gradient, this P2 region, this P2 flap. So in other words, this P2 flap is not performing as well as the other two flaps because it's further away from the airfoil surface. More of the boundary layer can bleed through, as I mentioned before, and that means that the region downstream of this flap is not segregated from the upstream region, and that means that that flow separation can really migrate upstream. That's what I think. Now, these researchers didn't go into that. They don't really provide too much flow phys information to draw any conclusions from, but from what I can tell, that's probably what is happening. If you have any other ideas, let me know in the comments below. So in table 3, they sum up a bunch of different airfoils with different flaps, showing the P0, P1, and P2, but also S1 and S2. Remember, S1 and S2 are those two flaps that are S-curves. S1 is where you have the peak first and then the trough. S2 is where you have the trough first and then the peak. Let me quickly scroll back up to these ones just to refresh your memory on them, on these geometries. So here we go, we have S1 here, peak, then trough, S2, trough, then peak. And they show the lift-to-drag ratio of these different wings with these flaps at different angles of attack. Now, interestingly, P2's performance, which is the one which is staged furthest away from the airfoil suction surface, dives hard at about 16 or 17 degree angle of attack. The other flaps give the airfoil lift-to-drag ratio of about 0.5 to 1 at these angles of attack, which is pretty bad anyway. But the P2 flap, which is the farthest away from the airfoil suction surface, ends up with only 0.14, which is much worse. So we can see that in this range, we are definitely in the stall regime and the postal regime, because we have such a low lift-to-drag ratio. You can see at an angle of attack of 11 degrees, the lift-to-drag ratio for all these airfoils with these flaps are around 8 to 9, and then it dives from there. And we can just see that's probably because this P2 flap is further away so that the stalled flow can migrate upstream, as I mentioned earlier. So interestingly, it can be argued that at moderately high angles of attack, so like 14 degrees or 15 degrees, these ones here, the P0 and S1 flaps perform the best, which is a little surprising because in S1, the peak comes first, which was shown in the last podcast to be detrimental to the drag. But its positive effects on the lift in this regime must be enough to overcome these negative effects to begin with, and still deliver a slightly better lift-to-drag ratio than a lot of the other cases. So in addition to this airfoil being staged up higher away from the airfoil and lower, they also looked at staging it like more upstream or more downstream. So figure 19 shows these configurations here. Here we go. So we have P1, P0, and P1. Now we're talking about this. P0 is where we have the flap starting at 80% of the chord, and P1 is where we have starting at 85% of the chord. It should be noted that the flap here does not stay the same length. It shortens so that the end of the flap coincides with the trailing edge of the airfoil. You can see here that the trailing edge always coincides with the back here. That's an important point as well, because this flap length may also have an effect which they don't explore here in this paper, but they just explore the effects of moving this flap further downstream and its effects on the airfoil's performance. So they are both straight flaps and angled down a little bit, but they don't say how much they're angled down. I'm going to say from this view here, they're probably going to be angled by about 2 degrees down. And in figure 20, they show that these flaps follow the same trends as we've found for pretty much the other flaps, but they do so to different extents. So in other words, in a pre-stall regime, these flaps again are reducing the lift, increasing the drag, so they're not favorable to the pre-stall regime. Post-stall, they increase the lift and reduce the drag to some extent. We've seen that quite a lot. And it can be said overall that putting the flap farther upstream increases its effectiveness for better or worse. So what I mean by that is, if you look at these graphs here, if you put the flap further upstream, which is P0 compared to P1, P0 always affects the airfoil's performance more than P1. So you can see here that this dashed dot line, the lift in the pre-stall regime is always worse, and in the post-stall regime always better, and the drag is always worse and always better in the post-stall respectively, compared to P1, which is further downstream. So depending on what you want, you may, like if you want to have just this flap affecting the airfoil a lot, then putting it further upstream is better than putting it further downstream. But if you want to mitigate the negative effects of this flap, putting it downstream more is better. And that makes sense because if you have it more upstream, it's affecting the airfoil more. That just is common sense. So for example, in the pre-stall regime, the flap that is farther upstream, so P0, makes the lift coefficient about 3 to 4% worse than when it was downstream by 5%. For the drag coefficient, it always doubled the increase in the drag compared to when you only put it down 5%, which is a bit of an interesting result because it's only 5% of the chord, but it makes such a big difference to the drag here. But on the other hand, when we were in the post-stall regime, when we put the flap closer towards the trailing edge, this flap had almost no effect on the lift. You can see here that it's like a very small increase, whereas when we put it at only 80% of the chord, it has a much greater increase. So here I looked at it and I found that it's about a 7% increase of the lift that this flap at 80% chord has. So in other words, putting the flap at 80% of the chord and extending it to the trailing edge and angling it down at about 2 degrees increases the lift of the airfoil at these postal angles of attack by about 7%, whereas putting at 85% of the chord, it effectively has almost no effect. And so moving that flap only 5% makes a big difference to the lift. I also wonder what would happen at even greater changes in the installation location. So if we were to put it even further upstream to like 50% or even 40% and like angling it so it almost hugs the airfoil surface but not completely, how that would affect the airfoil's performance. So overall, pushing the flap farther upstream by the 5% of the chord increases the effect of the drag coefficient by about 30% perhaps. So we can see here in this post-stall regime, it reduces the drag by 30%, and in this pre-stall regime by about that same amount. But regardless of where the flap is, whether it's at the 80% chord or 85% chord, the flap is reducing the drag coefficient quite nicely in this post-stall regime. So while we may not be getting any benefits for the lift coefficient, it does benefit the drag coefficient in this post-stall regime. And I'm not too sure why this flap location affected the lift coefficient much more for the drag than the lift. The authors didn't go into it, and we don't have any flow viz to analyze this. So we're kind of stuck with just trying with this information that we do have here and why we have this benefit for the drag but not for the lift. It may just be due to a reduction in the pressure drag overall, which doesn't really have much of an effect on the lift in this particular case because the airfoil is separating at the same sort of location, but the wake is maybe being controlled better with this flap. It's maybe angled down a bit more. So we still get the same amount of lift, but a reduced wake potentially. So in other words, the airfoil is separating over the same amount, but the wake is being controlled better with this flap. That's my best guess. I'm not really sure what else it may be occurring here because there's no other information. If you have any other ideas, let me know in the comments below. So that's the end of this podcast. We went through the second part of these flaps and how they affect the airfoil's performance. Let's quickly recap what we found here. So we looked at the effect of the flap when we stage it at different heights from the airfoil surface. So we have P0, P1, and P2 here, where we had P0 pretty much completely attached to the airfoil suction surface, P2 the furthest away by 0.16% of the chord, and we found that effectively the further away the airfoil flap, the further away the flap is from the airfoil surface, the less effect it has on the airfoil in the post-stall regime. In the pre-stall regime, it makes almost no difference. So that's a bit of a surprising find there. We also looked at the effect of changing the location of this flap. So we put it more upstream, more downstream, and we found that that has quite a big effect. So we see here, when we put it further upstream, it increases it reduces the lift even more than if we have it downstream, and it increases the drag even more than if we had it downstream as well in the pre-stall regime. In the post-stall regime, it's far more beneficial, where we have a greater increase in lift and a greater reduction in the drag. So the lift to drag ratio increases a lot here. So that's in this podcast. If you liked it, make sure to like it. If you want to see more like this, make sure to subscribe or follow it on Spotify or whatever you're listening to this on. And if you want to see more of these as well, check out our playlist. And if you want to get better at CFD and or theory yourself, check out our courses at the link in the description. And if you want to make your experiments 2 times more accurate, which is what happens when you accurately measure the density of air every day, then check out the Atmosphere Hawk. The Atmosphere Hawk is an instrument we make to accurately measure the density of air. And the reason why this is important is because the density of air changes by about 2 to 4% every day. So let's say you go into the wind tunnel in the morning and you do some tests, and then you go back after lunch and you do some more tests. Well, the density of air will have changed quite a lot in that time by about 2, 3, 4%. That's on a very normal day. If you don't take into account these changes, those are errors in your experiments, and unfortunately they effectively are random errors which you don't have any knowledge of, which means that they're the worst kind of errors because you can't really correct for them afterwards, and you also are not aware of them, which means that your conclusions that you draw with your data are erroneous just inherently. Now, these errors get even worse when you go from day to day, week to week, month to month, season to season. And changes of 15% are quite common. So you can have up to a 10 or 15% error in your data without even knowing it, which, like most aerodynamics these days, the changes in the performance of our objects are within 10% of each other usually. We don't find like 100% changes or 20% changes even. It's usually like 5%, 10%. So that means that those changes are within the error, which means that these changes are not really trustworthy when we find them, unless you actually measure the density of air. So the Atmosphere Hawk does that for you, and what's more, it makes your CFD validation data, which comes from experiments, more accurate, so you can rely on it better. So if you want to pick up an Atmosphere Hawk yourself and make your experiments accurate, check out the link in the description, and I'll see you next podcast. Peace, amigos.